Is my screen visible? Okay. Okay, so one thing regarding the last discussion that we had, so we will be continuing that discussion itself. So there was a mistake I had in this particular code where I said that the 6k plus 1 or 6, so every prime other than 2 and 3 are of the form this. This thing is correct, but the problem is with this for statement, as correctly pointed out by one of you. So instead of this condition, it should be something like I minus 1 into I minus 1 less than equal to n. So the thing is, I minus 1 can be a candidate factor, but you are checking if so if n is greater than I square, then you are discarding it. But it can very well be that the square of I minus 1 is less than equal to n, whereas I square is greater than n. So it will falsely identify those numbers as prime. So yeah, so this was the correction I was intending to make. Okay, so before jumping on today's topic, so is there any doubt from the last discussion that we had? Okay. Okay, so we will be talking about Fermat's little theorem today. So this is a very well-known theorem in number theory. So this basically states something like, so for integers a and p such that p is a prime and a is coprime to p. Okay, I'll write that down later. So this thing holds. So a comma a is some integer, p is a prime, and a and p are coprime. So first of all, can anyone tell me why this condition is important? Like what would happen if a and p are not coprime? So more specifically, can someone tell me what this value would be? Anyone? Any guesses? Any suggestion? What should lead to this? Okay, I'll maybe tell you. So p is a prime, right? So that means that if GCD a comma p is not equal to 1, then a is a multiple of p, right? So a to the power anything would be, let's put it alpha, would be congruent to 0 mod p. Because this is a multiple of p, and any multiple of p would give modulo 0 uh, with modulo. Yeah. This is clear, right?
Yes.
Okay, so I won't be proving this right now, but yeah, we'll be proving it if we have some time left at the end of the class. So now getting in some examples, you can check that 2 to the power 6 is congruent to 1, not 7. So what is 2 to the power 6? Can anyone tell?
64.
64.
64, which is indeed 7 into 9 plus 1. So it's congruent to 1, right? Similarly, you can check some. You can check 3 to the power 6, 4 to the power 6, anything. Mod 7 would give you 1 more. Okay, so this is mostly what Fermat's little theorem states. Okay, so maybe I can just put a box around it.
Sir?
Don't call me sir. I'm a second year undergraduate. Call me Anubhav. Yeah. Yeah. Hello.
Yeah, I didn't get the proof that you
No, I didn't prove it. It's like I just stated an example. So should I prove it right now, or like let's wait for the end of the class?
said. We'll do it after that.
Yeah. So it's not a very difficult proof. You can. So one proof is so the well-known proof is using group theory, but you can actually use induction on A to prove this. Anyway, so I'll be proving later. Now, do you remember one of the things that we postponed last class? So we talked about modular addition, modular addition, subtraction, and multiplication, but we didn't really talk about modular division, right? Now let's briefly talk about modular division. So okay, so I'm having Factorials mentioned next. Okay. Yeah, so I think I need more space. Okay, first of all, we want to the question we are tackling with right now is pertaining to modular division. So main question is, if you have two numbers p and q such that uh, q divides p, and let's just say p comma q. So they are non-negative integers. Then we want to find the value of p by q, not some integer m. So to make our life simple, we just want this number to be mod some prime. Okay, so m, where m is a prime. So you remember when I said that the numbers usually given in CP problems are primes. So here, so you can run a primality test to check that this number as well as this number both are very commonly used in CP problems, and both of them are primes. So now the uh, benefit of using primes is that you can actually get something called a modular inverse for every number other than the multiples of primes. So let's just briefly explain what a modular inverse is. So let's say you are having some integer, let's say a, and you're having some other integer b that are okay. So let's just take it from 0 to n, and this thing holds. A times b is congruent to 1 mod m, where m is a prime. Okay. Now we call so if this is the case, we say that b is the modular inverse, or modular multiplicative inverse is a more precise way of putting it. Multiplicative inverse of a modulo m. So now what this means is that whenever you have some multiples of k, multiples of a, let's say you are having some small c equal to some multiple of k a, so let's call it ka. A belongs to natural numbers. So now if you multiply b with this thing, c b, then you can actually get something like this, right? Which is congruent to k a b, which is congruent to k mod m, right? So like I'm assuming this is true. So somehow we magically have these two numbers a and b such that their product gives a modulo value of 1. Then if we multiply b with any multiple of a, then we can get k. So what exactly is k? K is nothing. So remember when we were talking about this, so we just solved this thing. Instead of p and q, we were calling them c and d. A divides c. Let's see. Now the question is, how do you get this value of b for a given a? So this part is clear, right? So if you magically have a b for some a, then you can compute any of its so you can compute c by a for any of its multiples c, right? Any problem in this? Okay, I think there are no doubts over here. Now let's write this down once again. Now notice that for p is a prime, so p is obviously greater than 1. So you can do something like pa into a times p minus 2 is congruent to 1 mod p. So this thing can be done, right? Multiplication. So I just broken this exponent into two parts. Now observe that this is actually your b that you were talking about. Just think about this for a moment. So we wanted a b such that a was congruent to a times b was congruent to 1 modulo n. Now if you take a to the power p minus 2 for, okay, so I've used p and m synonymously over here. So maybe I can use m all throughout. Where m is a prime. So clearly, this value of a to the power m minus 2 will give you the value of b. Anyone has any doubt in this? Okay, so let's do some examples of this that would make this clear. Okay, so can someone tell me what is the modular inverse of 2, let's say modulo 101? Anyone?
51.
51. So you didn't actually compute 2 to the power 99 for this, right? So, yeah, so it's pretty obvious, because what you want is some number over here in the left hand side that is a multiple of 2 and gives you a modulus of a remainder of 1 when divided by 101. So you chose to go with 102 and you have uh, calculated this value to be 51. Now you can check yourself that this value 51 is indeed equal to 2 to the 99 minus modulo 101. You can actually prove this in some other way as well, uh, instead of like doing the brute force of computing 2 to the 99. Okay, so let's maybe prove this. So this can be actually proved by something called uniqueness of inverse. So from the name, can anyone deduce what the statement should be? I'm pretty sure you have seen some kind of a thing in matrix multiplicative inverse, I guess. Okay, so it's something like if A so let's call them P1 and P2. If there are two modular inverses of this number A, then B1 must be equal to B2. Okay, not equal to, they have the same modular. Can anyone prove this statement? Okay, so it's a pretty simple statement to prove. So you have this thing, then you can just multiply E1 to the left hand side. Now, since this is known to be 1 from over here, so you will indeed have E1 is common to B2 1. So this means that the modular inverse is unique for any number m. So for this particular fact, we didn't even use the fact that m is a prime. So even for a composite number m, if you have some pairs of modular inverses, then those those inverses are unique to the other one. But for primes, the fun part is that you are always guaranteed to have a modular inverse. So if m is a prime, then you can always find a modular inverse of A, given that GCD of A and m are not 1. Sorry, GCD of m and A are exactly 1. So that means that of all the numbers in the range 1 to m minus 1, since m is a prime, every number over here has a GCD of 1 with m. So every number over here gives you a unique modular inverse with respect to m. Okay, so now
A and M are co-prime.
Sorry?
A and M are co-prime.
Yeah. A and M are co-prime, as I said over here. GCD of A and P. The problem I discussed is that if A is not co-prime with P, then the right hand side will actually be a factor of P, and that means that the left hand side will be a factor of P. That means that the right hand side will be 0. So yeah, this is needed, co-prime. Okay, now the only problem is for numbers like 10 to the 9 plus 7. You cannot just simply calculate this plus 5 for any A that you are given. Right, this so for using an algorithm such as for int I equal to, let's say m, let's say we put it this way, something like this, I is less than m minus 2 plus I, answer times equals, okay, so maybe you use this even A percentage. So this would be way too slow, right? What is the complexity of this piece of code?
O of m.
O of m, right? So O of 1e9 plus 5 is too much even for one number, but you'll see that you would need to repeatedly find out inverses for one particular property. So here we do something called fast exponentiation. So the main logic behind fast exponentiation is that you keep squaring and multiplying it with e if you are needing. So for example, you can compute something like e to the power, let's say, let's start with 17x. Okay, not 17. So to calculate e to the power 30, what you do is you write this in the form e to the power 15 whole squared. Okay, so maybe you write it e to the 15. Now the catch is you don't need to compute e to the 15 twice. You can only compute e to the 15 once and use that, like just square that to get e to the 30. So similarly, you can just compute e to the power. So this is for even numbers, and for odd numbers like e to the 15, let's write it separately. You can do something like e to the power, let's say 771, right? Yeah, there was some comment, I guess.
Yes, I was telling you 7.
Yeah. That's exactly what we can do. Okay, so yeah. Or we can simply write it something like a times e to the 14. And then this will automatically go to something like a power 7, right? So this way you can speed it up very fast. So you can actually compute e to the 30 by hand for some values, I guess. So a power 15, you can write it as, okay, so let's stick with a into e to the power 14. For e to the power 14, you can write it as a into e to the power e to the 7 into e to the 7. For e to the 7, you can write it as e to the power a into e to the 6. And you can go till you reach a or e to the 0, something like that. E to the 3, e to the 3, e to the 3 is a into a squared. A squared is a into a. So convince yourself that this is a lot faster than actually computing uh, a by multiplying a 30 times, right? So for e to the 30, if you just use this algorithm to compute this, it would be something like a power 30, a into a power 29, a power 29 would be a into a power 28. So yeah, you need 30 multiplications. Over here, you only need something like 1, 2, 3, 4, 5, 6, 7 multiplications. So can someone tell me how many multiplications do you need for any particular value of n? A rough estimate would be good, but yeah,
Log
can
n.
any? Okay.
Log n.
It's log
The base 2.
base 2. Roughly.
Yeah, so it's for n, shouldn't put an equal to sign. For n, it should be roughly order log n. So as you've seen that the base does not matter, but let's write it anyway. But can someone give an exact value of how many multiplications there are needed? Or like, can you just tell me if no such formula exists? Okay, I think you can think about this. So, like, I won't be spoiling the answer right now. So think about something like, I'll just give a small hint maybe, that every time you are either decreasing the length of the binary representation of a number by 2, or you are erasing a 1 from its binary representation. So just think about the problem in those lines.
Can you repeat once what you just said?
Okay, so I'm assuming that everyone knows about binary representations, right?
Yes.
Okay, so basically if this number is n, then what happens at each step is either one of these to happen. You either go to n by 2 if
Number
n
of
is odd.
digits in its binary representation.
You are close. Or it's n minus 1 if n is odd. So what I'm saying is that this corresponds to decreasing the length of the binary representation of n by just one digit. And this represents making the least significant bit of changing the least significant bit of n from 1 to 0.
Log n plus number of set bits.
Yeah. So it's something like log of n ceiling of that plus number of set bits. So let's just write it something like b of 1 of n. This is the number of set bits. Okay, so that is the answer I was looking for. Great job. So I've just put a small code snippet over here to just understand what's going on. So yeah, if this is so this code is a little different from what I have explained. Yeah, it's a little different from what I have explained. So I think you can change this line to something like long temp equal to. Okay, I'll just write it out first and then tell you what's going on. Return t into t. What I've written right now is basically the same thing that we were doing before. So if it's 0, if n is 0, so we just so we want to find a to our n. So if n is 0, it's 1 by default. So if n is odd, then we are doing something like a into a power n minus 1. That's what I've written. So fxp is the function. And otherwise, if a is even, you just find out a power n by 2 once and you return it, the square of it. So is it clear for everyone, this part?
Yes.
Okay,
Yes.
so the variant that I had coded initially, okay, so let me just. So this variant that I have coded, this is basically the same thing but in the reverse order. So over here you are computing it as this, right? So you are finding out the value of a power n by 2 once, and then you are multiplying it twice to get a power n. But over here, I'm just using this as like a squared times to the power 50. So this is a slight variant, but this is also something that works. So here I'm just writing it as e power 2 to the power n by 2. So here you have a power 2, and here you have n by 2. So this is also the same thing. You will see that. Is this clear? Okay, so is there a problem with this code? Anyone?
No.
So I'm assuming that this is clear. Okay, it might take some time to understand intuitively what's going on, but yeah, so this is a code log in that number time. So that means we can actually find out the modular inverse of any number in. So this can be sped up to order log n, right? So you can find any modular inverse in order log n time. That's pretty cool because order log of 1e9 plus 5 is, this is about 30. So this is much less than 10 to the 8. So pretty much you can do it for 10 to the 5 times or something. Okay, so that is all about fast exponentiation I wanted to cover. Now you can see that there are some other uses of modular inverse. So over here you have, okay, so don't try this problem right now, but I've just included the output of this problem, the output format of this problem for you guys to take a look. So here the answer is indeed a fraction. So this need not be a whole number, but this can be represented as a whole number if you multiply p with the inverse of q modulo this prime. Okay, so here it says that q is a positive integer co-prime to this thing. So this is very important, that q cannot be a multiple of this number. And then you can actually represent any number of the form, any fraction of the form p by q using this integer modulo this number. So you can actually check that addition, subtraction, multiplication in fractions are same as addition, multiplication, and let's say division as well for this particular way of representing. So more specifically, if you have something like p by q plus r by p, so if this is some, let's say a by b in normal arithmetic terms, then you will be having something like a b minus 1 is congruent to p. M. So you can just check this out once, I guess. I won't be proving it, but yeah, I think you can easily prove this by multiplying both sides of the up for this equality and this equality by b into q into t, something like that. Okay, so the point is that you can even handle non-integral stuff using p and q. Using modular inversion. So I hope that is fine. So I've just written a small code for the modular for finding the inverse of here. So it's basically the same thing I've said, that you code a function for finding a to the power n, and then you can just use that to compute mod minus 2 to get the modular inverse of a. So this is very important for many computer programming problems. So combinatorics is one of the key, let's say, a key topic where this kind of manipulations are used. So can someone again remind me what was the complexity of this entire thing? Let's say for finding
log
the
n.
inverse of log mod over here. Okay. So because we are finding the exponent of an object. Okay. Now in combinatorics, what you are, so everyone knows the one of these two notations, right? N or this thing, right? So what does this mean? This is C. Binomial coefficients. Can anyone?
Number of ways to choose R objects from N.
Number of ways to choose R objects from N.
Are distinct objects from n distinct.
Distinct objects from N distinct objects. And can someone tell me the formula of NCR or N choose R?
N factorial by R factorial and minus R factorial.
Okay. Is anyone saying something? Okay. It might be unmuted. Anyway, so the thing is that if you are asked to calculate something like, okay, so let's just get some more space in this. If you are indeed asked to calculate something like, okay, so find out the number of ways you can choose n r distinct classes from n distinct classes, distinct bases or something from n distinct vertices, classes, and you need to report this modulo m. Okay, modulo, let's say m equal to, as usual, 10 to the 9 plus 7, and you have some range like this, let's say. So can anyone tell me how to do this? Like, what will be the problem with blindly using this formula? So you calculate n factorial and then divide by r factorial. Like just normal integer division. Anyone? Like there's a very big problem with that.
Sir,
Yeah, don't stop calling me sir. Yeah.
can we use that formula that NCR is n minus 1, CR minus 1 plus?
So you want to use this formula, right?
Recurrence.
Oh, sorry, this one. Something like this, right?
Yes.
This was a formula, I guess, right?
Yeah.
Yeah. Okay. Yeah, you can. First of all, I don't think you can use this directly. Yeah, I think you can use this if n comma r is less than or equal to 10 to the 3, because computing this would be order n r, right? Just think about this maybe. Yeah, this is a very good observation. So like, this actually takes care of the problem that I thought some of you might know, that the division of this might have. So can anyone answer, like, why can't we just calculate n factorial and then just divide it by r factorial and n minus r factorial?
The numbers will exceed. Like the
Yeah,
limit.
yeah, exactly. So the numbers are huge. So even for, I guess, n equal to 50, you can't fit it in a long int, right? So these will overflow very fast. So you can do this way of solving, but there's a neater way of doing this. So first of all, tell me something. Can you compute this value, n factorial mod m? So how much time does it take?
Yes. O of n.
Perfect. So let's say if you wanted for all n, okay, let's write it j for all j in 1 to n. So what would be the time needed? So you have j stuff over here, n queries over here. So how much time would it take in total? Would it be order n into n? Order n for each factorial, and there are n instances. Anyone? Yes, no?
What is the question? Can you repeat?
So you need to find this value of j factorial mod n for all j in this range 1, 2, 3.
We can do in order of O of n.
And how would you do that?
I mean, start from 1 just for comparing n. We already have the factorial of n minus 1. So for n, we'll just multiply it with n.
Great. Okay. So everything can be pre-computed in order n, right? So you will have something like order of, you need some initialization of the fact of 0 is 1, then for all n. For I equal to 1, I is less than equal to n plus I. Fact of I is fact of I minus 1 times I percentage, something like this, right? I will be putting some amount of space over here. Okay, so let's not put some amount of space right now over here. Now my question is, so if you have computed all factorials modulo m for some number over here, can you do this thing? Return factorial of I, sorry, n divided by factorial of n minus 1. Yes, n minus r divided by factorial of r. Can you do this thing? So there was, yeah, so there was n factorial by r factorial into n minus r factorial. So can you just divide these factorials like this? And since you're taking mod, you have it well within your range of long ends or even integers, I guess. So the main question is,
We
can
need to
you?
use the modular inverse, right?
So why won't taking a normal division work?
Because it may.
It may. Okay, I think either one of us is having a network problem. So can anyone confirm if I am audible?
I mean,
Yes.
either I mean, if the factorial of n mod m may be also smaller than factorial of n minus r mod m, so it will give 0.
Exactly. So the main thing is that since you are taking this modulo, you are not guaranteed that doing the integer division or even a long double division, so a real division for two numbers would give you the same as the other. So yeah, so as one of you suggested, you can actually compute this, right? Minus 2 times mod minus 1. So this can be done. So what is the complexity of the entire thing right now? To solve this problem? Anyone? So what you're doing?
N log mod.
O of n log mod. I think you can write it this way: O of n plus log mod. Because over here you are doing an order n operation, right? And over here you are doing only one multiplication, which has two. Okay, so you are doing two multiplications where you have two instances of order log n or log mod operation. So it's something like order n plus order log mod plus order log mod. Right?
Yeah, N plus log mod.
N plus log mod. It's not n times log mod. Okay, now we can modify this question a bit. Let's paste this. So now you will be given q of this types of queries. So you will be given q occurrences of n comma r. Q occurrences of n comma r. And for each occurrence, you need to find out NCR. So what if I blindly use this algorithm over and over again? So what would be the time?
Q into
Q into
times
whatever
N.
there was, right? So any improvements that you can suggest? So if Q is also of this range, then you will definitely get a time limit considered for it. So any
We have already calculated the factorial of all n integers.
exactly. So we can pre-compute this for, let's say, 10 to the power 5, and then we can keep a separate function that has something like let's say n comma r that returns this value, right? Times, so I've been writing it as inverse factor minus r times inverse of factorial of n. So you can as well multiply these two and take their inverse and multiply that with factorial. So this should be r. And okay, there should be a semicolon after this, but yeah, you understand, right? So can anyone tell me the complexity of this program? Okay, so this blindly using this was order q n plus log n. But if you pre-compute all the factorials and then use this algorithm, then what is the total time complexity?
N plus Q log mod.
Order n plus q log mod. Okay, this is quite good, but my claim is that you can do much better. So the next trick is, okay, so you have pre-computed all the factorials. Now, why don't you calculate all the inverse of all factorials? So that is just having another array like inverse of factorial, which is basically inverse of. Right. So just inverse of factorial. So what would the inverse of factorial 1? Anyone? I fact. What would be the value of this? Okay, you can surely. Sorry, not this. Yeah, they would be the same. But yeah, sure, you can call this the function inverse of 1 and get it calculated. But yeah, it's pretty obvious, right? What would be the value of this? Anyone? Okay, I think there is some problem in understanding what ifact is. So ifact is another array that stores the inverse of the factorial of I with this, and this modulo mod would give you 1. So what, when multiplied with fact, 0 gives you 1? Anyone?
1.
Yeah, so it's just ifact
1.
is also equal to 1. Okay. And then you can just blindly multiply I factor n minus r times I factor. So now what is the complexity of this program? Okay, right, this includes. It's a bit. Okay, so this should be more. It's a bit complicated than just often. So there are 3 terms: n, q, and mod. Anyone? So it's clear that what I'm doing, right? Otherwise, please pick up.
n plus q plus n log mod.
N plus q plus n log mod. Okay. Yeah, this is not incorrect. But yeah, do you really need this n when you are having this n log mod? So this would simply be n log mod, right? Because you can write n plus. So let's just probably see why this is true. So q of n log mod is less than q of n plus q plus n plus log mod, which is less than q plus n log mod plus n log mod. So which is just 2 of this, which is less than 2 into q of n log mod. 2 plus q of n log mod. So just forgetting this. So this, the order of this is basically order of this, right? This is clear, right? Any questions? Any questions, comments, anything? I hope it's clear. Okay. So like, please be responsive. Otherwise, I think it's not clear, and you didn't understand it. Some stuff.
It is clear.
Okay. Yeah. So here's a code of what I've written. So yeah, I forgot it. Define. So just make it for I equal to 1 int I equal to I less than equal to max n plus n. So I've just done this thing. So factorial of I've computed fact, I've computed I fact, and then there is a function to have the inverse of a number using the function to get e power n. And then if, like, okay, so you probably know the fact that if r is greater than n or if r is less than 0, this is conventionally assumed to be 0. Right, so I've just returned 0 in that case. Otherwise, I've just returned it. Yeah. So you will notice that for these two, so first the multiplication is taken for these two, and after multiplying two terms, I'm taking a mod, and then I'm multiplying the third term. Why I'm doing that? Anyone?
To prevent overflow.
Exactly, to prevent overflow. This is a very important thing that you should do. Yeah, don't write program like this. Use a modulo over here and over here. Okay, so the claim that I made that this is actually better than this is not always true. So this for n and q comparable, in this case, that it doesn't really matter, right? Both are equal, but sometimes you will have q equal to less than equal to 1 is 6. That time you may have this better, and sometimes you will have q less than equal to 1 is 4 when you will have this. Anyway, let's move on. So you can do all sorts of stuff like computing the number of ways you can write, let's say, a string with small a number of capital A's, small b number of capital B's, and small c number of capital C's, given that a plus b plus c is equal to n. So this is the number, right? Everyone knows that. I hope so. Everyone knows this formula, right?
Yes.
The number of ways you can have A's, B, B's, and C's in a string. So you can compute all kinds of stuff like this. Okay. Now moving on to something which is not very closely related to number theory itself, but since we are talking about exponentiation over here as well, so let's talk about something called matrix exponentiation. Okay, now before I go into matrix exponentiation, so you people can suggest, maybe should I complete the proof of Fermat's little theorem and then move to matrix multiplication, or should I leave it for the end? Anyone?
Proof first.
Okay. Proof of okay. So we wish to prove that for some prime this happens, right? For a GCD of a comma p is equal to 1. So to prove this, I'll be proving that a power p is congruent to a mod p for all a. So forget about this condition. So this holds even for a's that are multiples of p's. It's obvious, right? So right hand side is also a multiple of p, left hand side is also a multiple of p, so this holds true. Otherwise, you can just cancel two a's out, and since a and p are co-prime, so cancelling is allowed. So you can get from here to this, right? So instead of proving this, I'll be proving this. So please speak up if there is a problem. So as promised, I'll be using induction on A. But before that, I will try to provide you some lemma that this value p choose r for prime p. So p is a prime as defined. I think I should write that p is a prime. This value is a multiple of p for r is strictly greater than 1 and strictly less than p. Can anyone prove this lemma? It has a short proof. Short does not necessarily mean it has an easy proof. Anyone?
Uh,
Yeah,
Okay,
if we
so-
even cancel all the factors, then it is always p in the numerator, right? So it is a multiple of p.
Yeah, exactly. So here this is r, this is p minus r. So this value is since r is strictly between 1 and p, so is p minus r, right? So this thing is 1 into 2 into 3 into up to p. This thing is 1 into 2 into 3 into up to r, and this thing is 1 into 2 into up to p minus r. So in this numerator there is this factor p, but in denominator neither of these two terms contain a factor of p, right? Because r is less, what have I written? Yeah, because r is less than p and p minus r is also less than p. So this is fine, right? So the numerator is divisible by p, the denominator is not divisible by p. So the numerator by the denominator cannot cancel this p factor. So p choose r is a multiple of p. So everyone clear with this?
Yes.
Now we will do something like, okay, so thesis is a equal to 2. I hope everyone is familiar with induction, right? It was in class 12, I guess. Okay. So for a equal to 2, you can actually do something like 2 to the power p is equal to 1 plus 1 to the power p, which is equal to summation of I equal to 1 to, let's start from 0 to p itself. We choose I, which is equal to we choose 0 plus I choose I equal to 1 to p minus 1. We choose I plus p choose p. Now can you see where this is going? This is okay. So okay, maybe I'll write it fresh over here. So let me even put this over here so that we are restricted to modulo p itself. Equal to, okay, sorry. This thing is equal to 1, I guess. Right? Yeah. Yeah, so r and p minus r are both less than p. That means none of them have a multiple of p. Okay, sorry for the interrupt. So now this thing over here should be a multiple of p, correct? Because each of its terms are multiples of p, right?
Yes.
Yes.
So this is equal to 1, this is equal to 1, and this is a multiple of p. So it's simply 2 to the power p is congruent to 2 mod p. So this statement holds true for a is sorry. This statement holds true for a is equal to 2. Now let's say a is equal to let's say that the statement a power p is congruent to a mod p is true for some n greater than equal to 2. Now we wish to find out this. So this again by binomial expansion is a power. Okay, so let's just write it this way. I equal to 0 to p. Choose I a power I, which is equal to 1 to p choose 0 plus summation of 0 to p p minus 1 a power I plus p choose p times a power p. So again, as usual, this entire term is a multiple of p since each of these are a multiple of p. So the entire summation is a multiple of p. So a plus 1 to the power p is nearly equal to 1 into p to 0 plus p choose p into a power p mod. Right. Now this is congruent to 1 plus a power p. And now using this, we assume that this is true for some a. So this is congruent to 1 plus a mod b. Okay, so everyone is fine with this proof. So if
Yes.
a power p is congruent to a, then a plus 1 power p is also congruent to a plus 1. There is a thing that I didn't quite rigorously explain, that why this implies this for a and so for coprime a and p, but I think you can figure this out. Okay, so we are done with the proof. Now let's move into matrix exponentiation. This is not really a topic that is very closely related to number theory, but yeah, it uses modulo, so you can very well include it into a number theory discussion, I guess. Okay, so now the main focus of this is that remember that we used an algorithm to get a power n. So this a was an integer, right? But this a can also be a matrix, and we can actually find something like a power capital A power n, where n is a natural number and a is some matrix, let's say 1 to 1. I don't know. So can you suggest a code that would do this? Anyone?
It's binary exponential.
Yeah, so you use the same code, and instead of, so let me copy this.
It will have different multiplication thought.
Exactly. Where was I was here. Yeah, instead of these multiplications over here, we can just multiply them as matrices, right? for this one. This one you can multiply it as a comma minus 1. So yeah, matrix multiplication, then you need to define what matrix multiplication is. So instead of writing it A asterisk A, you can actually write it something like for I equal to 0, I less than n, I plus plus, for j of the same value for k. So you know this thing, right? R I j is a of I k times b of kj. So this will give r is equal to a times b, provided that you initialized r with zeros, something like that. And you take the modulo at its state. Yeah, that is important. So the idea is clear, right? So I won't be following the exact code how you would do this for a function, for a structure that has a function, because you need to return this r as some data type that can handle matrices. But yeah, so this is the main idea. So does anyone have any doubt regarding the main idea? Okay, I think everything's clear. So yeah, so you can use this thing, to find the exponent of a matrix, but is it really useful? I mean, you can maybe do a lot of stuff that is never useful. Well, matrix exponentiation is actually a very useful tool. So maybe I'll explain this. So let's start with this very known example of Fibonacci numbers. So anyone, can you define Fibonacci numbers? Fi, let's say.
Fi equals Fi minus 1 plus Fi minus 2.
For I equal to,
I minus 1 plus I minus 2.
yeah, I is greater than equal to 2, right?
Yes.
F0 is 1, F1 is 1. This is the entire definition. This is the entire definition. Okay, so how would you compute f of n for a given n, let's say less than equal to 10 to the 5?
We will,
You can again pre-compute.
Yeah, you can pre-compute.
we
Also,
can also
yeah.
multiply a new matrix.
Sorry?
Means we can multiply a new matrix.
Exactly, that is what I was talking about. I will be talking about that, yeah. So here you can do something like, I'll write a pseudocode maybe. I from 1 to, let's say, n to the 5. Let's make it from 2 to n to the 5. So you pre-compute f of I, f of 0 and f of 1. So you can assign this. And then whenever you are required f of n, you will just report. So you can actually answer Q queries. Okay. So now the question is, can you do this at all? Okay, so I think I should be a bit more precise over here. So you are required to find for Q queries the value of this for some m. M is prime, usually 10 to the 9 plus 7, as you have seen. So you can just do this. Yeah. Otherwise, Fibonacci numbers grow really, really fast and you can't fit them in long longs. Even at n equal to 50, I guess I don't know. Yeah. Okay, now the question is if q is less than equal to 10 to the power 5 and n is less than equal to 10 to the power 80. Now, is it at all possible to find this value? Okay, so someone was suggesting something regarding some new matrix or something. Can you please tell us now?
we will prove this for the new matrix.
Properly audible. Can you speak a little louder?
This means we have to show means how we are getting the new matrix.
New matrix as in?
Means there is F1, F2, so we will try to multiply it by a matrix and we will get the next two terms.
Exactly. So, okay, so maybe let's start with F0, F1, okay?
Mhm.
Okay, so, yeah, okay. Now what you are doing to multiply something to get F1, F2, right?
Yes.
Yeah, so this is the trick that I was talking about. So instead of writing this as F1, F2, you actually put in the recursion of the largest term over here. F1 plus F0. This would give you something like 0, 1, 1, 1, right? So this is basically 0 into f of 0 plus 1 into f of 1, 1 into f of 1, f of 0 plus 1 into f of 1. So this is f2 and this is f1. In fact, you can actually make this equal to n minus 2 and n minus 1. And you can get this, right? To n minus 1, n minus 2, n minus 1, which is equal to f of n minus 1 comma f. Okay, so now what were you suggesting? Okay, so I'll just continue, I guess. So to find f2 comma f2 f1, this row this column vector, you can multiply this matrix. Let's just call this to be A, and let's just call this thing to be maybe f of capital F of. So you saw that you can do something like this, right? F2 is equal to A into F1, right?
So means
Yeah, sorry.
means for the further terms we will try to raise the power of A.
Exactly. So for F3, this is F3, F2, sorry, F2, F3, which is equal to A into F2, which is further equal to A into A square F1, right? So you can actually find this relation that F3 is equal to Fn is equal to A power n minus 1 F1, right? So now the catch is that you can use matrix exponentiation on this particular matrix. Then when you get something like an is equal to an minus what did I get? Yeah. So an minus 1 is equal to let's say a, b, c, d. Then you know that f of n minus 1, f of n is equal to a, b, c, d into f of 0, f of 1. Okay, so I think f of 0 should be 0. Yeah, so there was, yeah, I mistakenly wrote this as well. This should be 0. Yeah. Okay, so you can actually find this in order log n, log n, and then you can just okay, so you can just find the value of fn by just taking this term, I guess, right? Is it f of n is, yeah, I think it's just d, right? So you just report this and you get the value of f. So is it clear what I'm doing? Anyone?
Once can you go over it again?
Okay. So these equations are clear, right? Yes, no? Okay, I'm assuming that these aren't clear in the first place. Okay. So is this equation clear?
Yes.
Yes.
Okay. So I just abbreviated this matrix as A and abbreviated this as f of n minus 1, this as f of n. This is what I do. So from here you have f of n equals A times f of n minus 1, right? Clear?
Yes.
So I just put n equal to 1 to get this. And now I just increased it from n equal to 1 to n equal to 2. So I got this formula. And then I wrote this as A into F1. So putting that over here, I get this A squared times F1, right? Is there a problem with
Yes,
this?
yes. Fine.
Okay. Similarly, you can do stuff like if f of 4 is equal to A cubed F1, f of 5 is equal to A cubed, it is about 4 F1. So in general, you can have this, right? Is there something confusing?
No, fine.
Okay, now the thing is, if you can compute this e power n minus 1 using this fast matrix exponentiation that I was talking about, and let's say you get a 2 by 2 matrix that is of the form A, B, C, D. So you're guaranteed to get a 2 by 2 matrix, right? So any n by n matrix when x raised to some power, its dimensions remain the same, right? So when you are raising this A, so this particular matrix, to the power n minus 1, you get some A, B, C, D, or 2 cross 2 matrix, right? So this matrix you can get in order log n. Is that correct? You use this
Yes.
fast exponentiation.
Yes.
Yeah. Okay. Now when you have this, you simply write down f of n is equal to a power n minus 1 times f of 1, right? This is the formula that we started with. Well, we didn't start with, we arrived at over here. So now you just write the expanded form of this over here. So this is f of n, this is f of 1, and this is e power n minus 1, right?
Yes.
So now you just put in the values of f of 1 and you will get something. So this is the value of this, which is equal to, I don't know, BD, I guess, right? I hope I'm not making some arithmetic mistakes over here. Yeah, it seems so. So f of n is equal to d. Okay. Yeah, so please tell me if you find that I've done some mistake or it's not clear.
It's clear.
Okay. So just raise this matrix to the power n minus 1 and then take the bottom right element as your. Okay, so it's 7:30 already. I think we put a stop to it. There were a couple of topics that I would had like to talk about, but they are not really important. But yeah, I mean, you guys might very well know about prime factorization and a number of factors. Okay, so I'll be asking if there is any doubt slash suggestion slash comment regarding today's discussion.
I have a doubt, means not regarding today's lecture.
That's okay.
I read earlier in gigs for gigs that for calculating the modular inverse, we need to learn something called extended Euclid algorithm. Why do we need that if we can use this?
So in this algorithm, you remember that we had a very important fact that this P was a prime, right?
Yes.
So that makes our life a lot simpler. So the GFG article that you have read is basically finding out the modular inverse for any number A and any modulo n. Right. So this need not be prime. So then you can do something called a Euclidean, extended Euclidean Euclid's algorithm to get this value of P, provided that GCD of A comma n is equal to 1. Otherwise, you can never have a modular inverse. So just think about this, why you can't have a modular inverse if this condition fails. Can't have some number, let's say P mod 14. Just think about this once. Okay. Yeah, extended GCD, extended Euclidean algorithm. Those are very intriguing parts of number theory. But given that your where did it go? Given that your numbers are usually 1e9 plus 7 and 998 3432. I forgot that number. I think it's 998. Where did I put it? Yeah, here. 998 244 These two are both primes. So you can use this technique. Extended GCD does appear in computer programming, but yeah, it's a bit advanced.
Okay, understood.
Okay.
Can
Anyone
you
else?
can you give some questions means which are directly
Oh yeah.
related application of that?
I did put in some examples over here. Okay, so I think I can share this document. I think I can paste these questions.
What is the topic for next class?
Moinak, are you there?
Yeah.
think-
The next class will be we'll be covering the basics of STL. So like the data structures like vector, stack, queue, all those data structures, and we will also cover some STL functions like sort and stuff like binary search and lower bound, upper bound. So yeah.
Okay.
These STL are in C or C++.
STL is a part of C++. So like it is assumed you have some knowledge of C++. I mean, whatever you know from C is also okay. I'll just it won't be difficult if you know C, I think. Yeah.
Uh, Is the class in Saturday only, like same timings?
Yeah, it will be on Saturday only.
Okay.
Okay, so any other questions for these topics, or any suggestion that you might want to put up, any feedback, anything?
Can you provide me name for some book?
Your voice is too low actually. Can you speak up a
Can
little
you
louder?
suggest some books for people?
Suggesting books for this. Is that your question?
Yeah, for maths.
Okay, so I mean, the most part you would get just by googling stuff. So that is the main source of. But like for CP related maths, so there are two books that are very popular in the CP world. So one is the Competitive Programming Handbook, I guess. The Competitive Programmer's Handbook, I guess. Uh, I forgot the writer's name. Moinab, do you remember the writer's name?
It was some hard to pronounce name. Wait, I have a link to it. Let me
Yeah,
just.
to provide a link to it. And there was another book called Competitive Programming.
3.
Yeah, I mean, I think 3 is the edition that is popularly available online, but yeah.
Stephen Elim. Stephen Elim.
Stephen Hallett, yeah. So yeah, you can check out the number theory portions, but the ultimate rescue is offered by Code Forces and the blogs it has. So you should go through Code Forces blogs and the blogs at cplalgorithms.com. Also in GFG, you can find some topics like someone suggested extended Euclidean algorithm.
Uh, we should use Podge or like code forces now.
Personally, I'm a little biased to Code Forces, but yeah, Spodge is, I think, equally good. I mean, yeah, Moina, do you want to comment on this, I guess?
Not really. I mean, I have barely used Sphere Online Judge.
Yeah, same with me. Like, I have not used Spodge a bit, but yeah, the problems that I've solved in Spodge are quite classical, and it's a good place to learn classical problems in this. Yeah, so you can use Spodge. There is no harm in using either of them. But in Code Forces, there are more problems that you can solve, I guess. I
Can
don't
you
know.
give
The
some
opinion is biased. Yes.
in typing speed? Means I am able to think the code, but I am not able to type fast.
Oh yeah. So this website called kivia.com. That is my favorite. Kivia.com. Yeah. For typing. This is a very good. Okay, so ideally, in your free time, like by free time I mean in semester breaks, you can go like 1 hour or 1.5 hours per day. But regular days, I think 30 minutes is sufficient. 30 minutes for 1 week, and then you can even slow it down.
What is the ideal speed?
That's it should be as good as you can do. And also like uh, the typing speed in writing just plain text is not a very good measure of the typing speed of writing code, because there are multiple special characters, tabs,
Yes,
indentations.
and those are also tested, no, in this site which you give. Means
Mm, I I think there is an option, but yeah, I'm not sure. I don't use that. Yeah. Like I don't use that option. I only practice using the normal text-based typing. Yeah, but they have a monotonic relation, right? So if your normal typing speed increases, your code typing speed also increases. So maybe try to hit at least 50 or 60 by 1 month. By 50 and 60, I mean 50 or 60 words per minute. Okay. Someone said
What can be an ideal rating which you could target in code chef or code forces by the end of the first year?
that is also a uh, very vast question that you have. Okay, so maybe so. Did you have programming in class 11 and 12?
Yes,
No.
I had 9 to 12.
Okay, so if you are familiar with programming in your high school, then I think you should get up to, I don't know, 1500, otherwise 1300 in code forces. Moinak, is that a good estimate?
What?
So, like, they want to know what is the ideal rating that they should have at the end of the first year.
That is a very difficult question.
Yeah, so
Uh,
that is something that depends from person to person. It's like, I mean, don't have a particular target right now. Maybe try out some 2 or 3 contests on code forces or code chef. Then your rating should maybe increase by 200 or 250 at the end of this particular semester, or maybe after a year. I mean, yeah, don't think too much about the rating right now. Okay. I know the answers might not completely satisfy you, but yeah. Any other suggestion, feedback?
Means one more question. Which I have, the thing which you have learned about CP and all, are these taught in CS branch, or means you have learned it by yourself?
Not in not entirely. They are not entirely taught in the CS curriculum. So there will be a course called Algorithms One that I think. So CS people have to do it, but I think other uh, students from other departments can also take it as an elective. But yeah, it's neither necessary nor a sufficient course that you should have to get good at computer programming.
By the end of like this session, means like the 2 months, we'll be proficient in that Algo 1 course.
What do you mean provision?
Like we'll have the CS people will have the course in second year, no?
Yeah,
And after doing this CP course, will it become easier?
yeah. I think I hope it does become easier if you want to. Uh, okay, so if you are in a computer, if you are in the department of computer science, then yeah, I think it should be easy. But yeah, Algo One is not a very easy course as per popular opinion. Anyway, don't get too much about course curriculum right now. Yeah, our aim is to basically make you make a mindset that will at least enjoy the Algo One course. I hope it becomes easier. Yeah, that is also a part of the consequences that we are intending to achieve. But yeah, that is not what we are aiming for right now.
Okay.
Okay. Any other question?
For GOC means do we have some selection procedure or something like that?
Oh yes, you will be having a selection. Not pretty soon, but yeah, it would be soon. So there would be a contest, and then there should be an interview round. Okay, so
Okay.
Will it be completely coding based or something else?
yeah, so the contest is a coding contest. It's a CP contest. So have you given contests like starters or code forces diff 3 rounds?
No.
Okay, so I think you should start giving those contests. So basically, the structure of the contest would be the same. The difficulty level might change a bit. Uh, yeah, so the point is that you would be asked to code and submit your codes, and your codes would be checked with automated input-output systems, and then
Code
if you're sorry,
like code night.
I still didn't get you.
I'm telling like code night. Yeah.
Yeah, so you have participated in CodeNet, yeah. So it's like CodeNet. But yeah, it's a difficulty level may differ slightly.
Can you keep like that after this semester? Like this semester is going really hectic.
Okay, so I can definitely pass on that information to seniors. So can anyone just tell me what is the intended NSIM rates for this semester?
It will finish in June 24th around.
Okay, so you are recommending that we take it after June 24th, right?
Yes. Means June, means mid-July, because we need to practice also.
Okay. Okay, like don't take it so seriously that you need to practice. But yeah, enjoy the contest. That is the thing. Yeah, sure. We will maybe talk to the seniors about making the contest at June. Sorry, mid-July. That can be. So I'm not promising that it would be done, but yeah, we would convey that to the seniors. Any other question?
By the way, tomorrow there is a Code Forces Division 3 round, so if you want, you can participate. I mean, I would recommend taking part in it because it's good practice. Yeah.
Yeah, please take part in it if you can. Okay, I think everyone is done with the questions. Okay, then we can call it a day. Okay, so thank you everyone for attending. It was